Hello and welcome. In this video I want to just fill you in on some definitions regarding curves and regions in the plane so that in subsequent videos when we talk about um, vector fields and when the vector fields are conservative, we'll have these definitions already in our vocabulary. So here we go. A curve C is called closed if there exists a parametric representation, R of t, for t between a and b, with r of a equals r of b. That is, it's closed if it starts and ends in the same place, right? That r of a equals r of b is the ending point, the starting point and the ending point are being sent to the same spot in the plane. This curve here, for instance, is closed. Right? Another definition here, a curve is called simple if there exists a parametric representation for t in the interval, in the closed interval from a to b, such that r of t is 1 to 1 on the open interval from a to b. Okay, so first of all, interval notation. This with the square brackets is the same thing as that up there. It includes the endpoints, where with the open parentheses here, it does not include the endpoints. Okay. Now, there's also the matter of, I just call this a closed interval as opposed to a closed curve. A closed interval is an interval, on the real number line that contains its endpoints, where a closed curve is defined to be just exactly what we said here. It's a curve that starts and ends in the same place. So I'm using the word closed in a couple different ways there. But there's closed curves and there's closed intervals. The open interval does not include its endpoints. So what this is saying is this curve could only, to say it's 1 to 1 means that two different inputs have to give you different outputs, with the exception of it's not saying anything about the endpoints. So the endpoints might give you the same output. So scrolling down here, I have, as we saw here, this was a closed curve, but it's not simple because it crosses over itself a couple of times. This curve here is simple, but it's not closed because it starts and ends in different places. Right? This curve, here's a couple more curves. This next curve is neither simple nor closed, right? It's not closed because it starts and ends in a different place, and it crosses over itself somewhere in the middle. It's not simple or closed. This one down here, this lovely thing, is both simple and closed. Simple has nothing to do with how convoluted it's drawn, right? It's just a matter of, does it cross over itself? If it does not cross over itself, it's called a simple curve. And if it ends where it begins, then it's called a closed curve. Okay. Yeah. There you go, a simple closed curve. I like that one. All right, so now a couple of definitions regarding regions. The first definition is to say that a region is connected. So a region D in the plane is connected if, it's a connected region, if for each pair of points P1 and P2 in the domain, in that region D, there is a path between P1 and P2 that is also entirely contained in D. Most textbooks I've seen call this path connected, although the textbook we're using currently is calling it connected. Right? There is another definition that's generally used for connected involving open sets, but this is fine. Connected, if you can find two, if for every pair of points there's a line, there's a path between them. So for instance, I could take a point here and a point there, and there certainly is a path between them that's contained within the region. However, there's also a pair here and here where any path between them would have to leave the region for a while, and there isn't any way you could get from P1 to P2 here and stay completely in the region. So this region is not connected. Down here, pick any 2 points in there, then yeah, there's a path from one to the other, and that is connected. Now we have a notion of simply connected. We say that a region D in the plane, that should be P-L-A-N-E, is simply connected if any closed curve in D can be shrunk continuously to a point while staying entirely in D. Let's scroll down and see what that means here. So here's a couple of regions. This one right here, this looks like a region with a hole in it. It is connected, right? That is, you can take any 2 points in here and you can find a path from one to the other that stays completely in there. But to decide whether it's simply connected is you're looking at, what was the definition again here? That any closed path, so if I have a closed path in here, could I shrink that down continuously to a point? So could you make that smaller and smaller and smaller? And yeah, that would shrink to a point. There certainly are closed curves that do shrink to points. But if you took a closed curve that looked like this, there's no way you're going to shrink that path down to a point without at some point going outside of the region, because you'd have to shrink down through this part in here, right? And that part in there is not part of my region. Okay. So that is connected, but it's not simply connected. The one up here, this is definitely simply connected. Any closed path that you happen to draw in here could be continuously shrunk down. Just think of it like a, like an elastic band that's been really stretched to do that, and then it would just shrink right down. You could pull it right back to that point, let's say. Simply connected, not simply connected. Both of them connected, but because this has a hole in it, it's not simply connected. Essentially, if you got holes in the middle, it's not simply connected. The textbook has one example that they don't give an answer to. They just ask the question, is this region simply connected? And they essentially have a circle and then another circle inside that's tangent to the first circle at one point there. And my question is, I will answer whether this is simply connected or not if you tell me whether the boundary is part of the set. That is this a closed set that contains all its boundary points, or is it an open set that does not contain its boundary points? Because the answer is different. If this is an open set so that none of the dark blue on the edge is contained, then that point of tangency there is not contained in the set either. And that would be a simply connected set, because you couldn't get a path that goes around that circle because the point would be missing that would be required to get around. On the other hand, if the edge is included, so if this is a closed set, then you could draw a loop around it and hit right in that spot there and go through, and then it would not be simply connected. So the answer here is yes, it's simply connected. If it's an open set, no, it's not simply connected if it's a closed set. Right? If you include that boundary, then it is not simply connected. Okay. So that's it for this video. Just a couple of examples, or sorry, a couple of definitions about paths being closed and simple, and regions being connected or simply connected. Enjoy.